great. So let's, well, a lot has happened since we last met. Reading week, how was reading week for everyone? Did you all take my advice and relax a little bit? Okay, good, that's good, that's good. That's important, right? That's why we have it. Keep in mind that your brain is a muscle, right? It's muscle tissue. So like any other muscle in your body, if you're just constantly working it, it's not going to help, right? That's why studying the night before the midterm is a bad idea, right? Because it'd be like if you went and like did some crazy workout before like the night before running a marathon. Like it's not a good idea, right? Because you're going to be fatigued in the morning, right? That's why you shouldn't study the day before a midterm. It's a bad idea. There's actually, especially in adults, particularly in adults over, I think, 17. Little bit of neuroscience. There's this cells called glial cells, and they surround your neurons. So as you get older, these glial cells are sort of like solidifying pathways in your brain. They're like gluing certain neurons together. And those glial cells appear at night, interestingly enough. So what happens, this is a very random side topic, but what happens is you have your neurons, which sort of like lead to each other, right? Pass information along each other throughout your brain. At nighttime, it goes backwards. So it's solidifying pathways that you use throughout the day at night. That's why it's so important to sleep. That's why sleep is really good for learning, right? Because if you don't have those pathways solidified, you might remember it like for a few minutes, but you won't remember it for a few days or a few months or a few years, right? So it's these going backwards piece. Your body, as you get older, gets good at building those pathways and solidifying them in what are called glial cells. Very important that you sleep before exams. Okay. Speaking of exams, how did the exam go?
It wasn't too bad.
Not too bad? Okay, that's good. I'm glad to hear. I think it was all fair stuff, right? Like there was nothing like where like you would have seen it and been like, what is this, right? Like it's stuff we've been doing. So hopefully at least. So yeah, hopefully it went well. So I'm grading them now. And I think probably not next week, but maybe the week after. Should expect them back, I'd say. Just because of the timing on it, it's kind of poor timing. Okay, moving on. This week we are talking about cardinality, algorithms, growth of algorithms, and divisibility, and a little introduction to mod. But really we're going to focus on cardinality and growth of functions. So cardinality, what is cardinality? Any idea?
Just like the number of elements in the set.
Yeah, it's like the size of the set, or the number of elements, right? Or something along those lines. So typically we denote the cardinality of a set like that. Just as a little side note, we use E often for a set, a general set. You'd think we might use like S. Typically we use E. And the reason is because set theory was pioneered by French people. E is ensemble, right, for set. So yeah, that's why we use the E, if you ever see that. E usually means a set. There's 3 different types, or like sort of categories for cardinality. Anyone know what they are? Sort of classifications. Yeah, so we have finite, we have countable, and we have uncountable. Yeah, so 3 different categories, right? Finite's pretty self-explanatory. It's like a number, right? The output's a number. So for example, the cardinality of the set 1, 2, 4, 7 is 4, right? There's 4 things in it. Countable and uncountable are both types of infinite. There's basically 2 different types of infinite, and they're different in size. Any idea what countable means? If I say a set is countably infinite. Any ideas? So basically it's in the name. It means I can count the things in the set. If I had infinitely much time, I could come up with a method in my head so that I could count them all, list them all out, right? So as an example, the set of natural numbers is countable because I could go 1, 2, 3, 4. If I had infinitely much time, I would hit every single one. I wouldn't miss any, right? Found a way to be able to do that. It's pretty easy. Now, a set that's uncountable might be the real numbers. So if I were to count out the real numbers, I would say, well, maybe I'll start with 0. It's a good real number. What comes after 0? Well, 0.000001, maybe. Well, what if I add another 0? I missed one, right? You could always keep doing that, right? So there's no, you can start with 0, but what's the second number you would say, right? I don't know. It's uncountable. You can't count it. Make sense? Cool. More mathematically, we say that a set is countable if there exists a one-to-one function from that set to the natural numbers. So it kind of makes sense, right? Because if you can count it, then you're going to count the one thing first, and then another one second, and then another one third, right? So that's kind of your one-to-one map, is like you input which number, and I'll tell you which number in my counting or whatever, right? Does that make sense? We're going to do some examples of it, but before we get to that, I want to talk about growth of functions and modular arithmetic briefly. So there's 3 sort of different ideas here for growth of functions. So sometimes we might say a function is big O of f of x. Sometimes we might say that a function is big omega of f of x. And sometimes we might say that a function is big theta of f of x. Any idea what the differences are between those? Oh, it wasn't on your exam, so that's probably still good to know. I think it's going to be on a Canvas test, is what I heard. I might be wrong. So big O is like the worst case of an algorithm. Big omega is the best case. And big theta is the case where the worst case equals the best case. So they're actually just one case, right? It doesn't matter the specifics of your problem. So usually you're thinking about like an algorithm or some sort of function that we're considering here. And so as an example, say that you have a function that takes in a list, right, and does something with it. Try and think about like if you add things to that list, make the list longer. Like how does the difficulty of the problem change, or how does the time complexity of the problem change, right? So as an example here, if this x-axis is the number of items in the list, and the y-axis is the difficulty of the problem, like difficulty for a computer, maybe as you add items, it gets like more difficult with each item you add, right? That would be maybe like n squared, because the graph of this function might be n squared, like the square function, right? As you add items to it, the difficulty grows quadratically, right? That's not good. You don't want that, right? You want something that's like, you know, as low time complexities, or complexity in general, as possible, right? So that as you scale it, it doesn't get bogged down, right? And then modular arithmetic, the last thing I want to talk about, divisibility. So we say that if we write that B is divisible by A, what we mean by that, so we use that vertical line to mean divisible. What we mean by that is that B times some number K is equal to A. Is that right? Backwards. Thank you. That way, right? Read it out. B is divisible by A. So that means A times something equals B, where K is some integer. So that's divisibility. It's kind of straightforward. So as an example, like 3 divides 6 is true, right? Another one is, what am I looking for here? Modular arithmetic. So we often write something like A is congruent to B mod n, where A, B, and n are integers. This is the same thing as n divides A minus B, right? The reason for that is that this mod statement is like remainders. So say that A was equal to something times n plus some remainder. A and B have the same remainder when divided by n. They don't necessarily, K and L don't have to be the same here, but they do have the same remainder. I don't know why I put a equal sign there. Plus. Yeah, so they don't necessarily have to have the same like multiplier here, but they do have to have the same remainder. If you subtract those, you get like something that's like K plus L, or sorry, K minus L times N, and then the R's cancel out. So it's some multiple of N, right? So then you could apply this idea over here, and you would get A minus B equals K times N, right? This is useful for proofs, yeah.
I'm pretty sure it's B minus A, not A minus B, or like the definition.
It doesn't matter. It doesn't matter. Like here, you're saying?
Yeah.
Yeah, it doesn't matter because A is congruent to B is the same thing as B is congruent to A, right?
Yeah.
So it doesn't matter which order you do it. It would change things, but doesn't matter definitionally. But yeah, does that make sense? So for proofs, try and get stuff down to these equations, these bare bones here. Work with the equations and then translate it back into the form you need. Okay, I think that's all I have for talking here. I'm going to stop the recording.